Now that we've got a good idea of how the solar system began, it's time to get started to investigate in more detail the various planets within it. Since we know the most about the terrestrial worlds, we're actually going to devote 2 lectures to them. At this particular lecture, we're going to look first at their interiors, and then in our next lecture, we'll look at their surfaces. We're going to see a great variety of different landforms and features. How can we possibly know what's happening inside of the Earth? Well, geologists have developed techniques to enable us to probe inside of the Earth. They measure the earthquakes that occur and other various techniques, and these allow them to determine what's going on inside and the interior structure of the Earth. As you can see in our first diagram here, essentially the Earth's interior can be divided into 3 main sections: a higher density core, a moderate density mantle, and a lower density crust. Why is that? Why is the interior separated in this way? Well, this is due to a process called differentiation. Differentiation simply means that gravity is going to pull slightly higher on higher density material than lower density, and as a result, the higher density material is going to gradually migrate towards the center. The lower density material instead is going to gradually float towards the surface, and therefore we have these 3 basic regions of the Earth. Now it is obviously a bit more complex than that, but this will suffice for our purposes. So geologists have been able to tell us a lot about the interior of the Earth, and we certainly don't know nearly as much about the interior of other planets because we can't observe them directly as we can Earth. However, we can use what we learn here on Earth to model what is likely happening inside of other planets. And this is a great bonus for astronomers to be able to do. Planetary scientists can take what's learned here on Earth and again apply that to the other planets. So let's talk a little bit about the geology and the activity of different terrestrial worlds. Where does all the energy come from for powerful earthquakes, violent volcanoes? It comes from heat inside a planet. Heat is what drives geologic activity. Well, where does the Earth and other planets get that heat from? There's 3 main ways that heat originates in a planet. As you can see here, number 1, early in the history of the solar system, impacting planetesimals carried tremendous energy with them. Their velocity as they crashed into the early planets would have been translated into thermal energy, heating up the inside of the planet. As that tapered off and the planets began to age a little bit, another process began to kick in. We just mentioned it, differentiation. Here again we have the denser material gradually working its way towards the center and the lighter material gradually moving towards the surface. This process can actually release a significant amount of heat. Over time, of course, the planets again become segmented into the various sections that we saw, and the point is that process begins to slowly fade as well. But today there is radioactive decay of elements inside of Earth and other planets, and this generates a considerable amount of heat. Where does all that heat go? Well, this heat normally wants to travel outward from the center. The planet is hottest at the center, and that heat wants to work its way outward. How does it do that? Well, there's 3 main ways. Number 1, convection. This is where the actual rock is itself moving towards the surface. Just as hot water wants to rise to the top of a pot, hot rock wants to rise towards the top or surface of a planet. Number 2, when that hot rock begins to come in contact with other cooler rock above it, perhaps the crust, it's going to conduct the heat. Just as like perhaps you put your hand on your car on a cold winter day, the heat flows out of your hand into the car, or vice versa. If you put your hand onto your car when it's a very hot summer day, the heat flows out of the car into your hand because, again, they're in contact. So here we have the hot rock, again, reaching cooler rock, and when they're in contact, the heat is transferred. Finally, that crust then, as it receives its heat, radiates it into space, very much as perhaps a small electric heater might radiate heat out into the air. So this is how that heat gradually escapes. Now, of course, the escape must be balanced with the amount of heat being generated for Earth's interior to remain in balance. Interestingly, the size of the planet has a great effect on the amount of heat and how long the planet will retain that heat. You can see in our diagram here we're comparing Earth and Venus and Mars and Mercury and the Moon. Earth and Venus being quite large, they generate the most heat and they're able to hold on to that heat for longer periods of time, and as a result they remain geologically active for much longer. The time the heat needs to escape depends on the surface area divided by the volume, and so in a sense a larger body is going to cool more slowly. A smaller body is going to cool more quickly. And as a result, you can understand that a larger body, again, will remain geologically active longer. A smaller body will not. So we would expect the smaller terrestrial worlds, the Moon and Mercury and even Mars, to gradually cool off, lose much of their internal heat, and not be very geologically active at all. We would not expect to see volcanoes and earthquakes currently happening there. But on the other hand, a large terrestrial world like Earth will not only generate more heat, but it will hold on to it longer, and this will continue to drive geologic activity today, as we do see on Earth. There's one other very important factor we want to touch on regarding the interior of planets, and that is that, again, as this denser material moves to the center, this is where you get your denser rocks and especially metals. So we believe Earth's core is composed greatly of metals. Metals, as you know, conduct electricity, and so if you get these metals moving as the planet is rotating, this moving molten metal will generate a magnetic field. Now that magnetic field will expand out beyond the surface of the planet, and this will have a great effect on the planet. In our case, Earth's magnetic field establishes a region around the Earth that we call the magnetosphere. And this is very important for us. This magnetosphere protects us from harmful particles from the sun, which would not only injure you and I, but would importantly damage our atmosphere, which of course we rely on, don't we? So this is very, very important for life. For a planet to have a magnetic field, that would make it much more habitable. Perhaps a few of you might have seen the famous northern lights that we see in the polar regions of Earth. Here's an actual example where a little bit of those particles is able to get through the magnetic field at a weaker area, and the energy lights up the air, so to speak. And we see these beautiful northern or southern lights. Well, that's an indication, again, of those particles reaching our atmosphere. Well, let's go ahead and take a look at each of the terrestrial worlds then, and just take a brief glimpse inside of them. Here you see the interior of Mercury. Mercury being rather small, near the sun, of course, is very hot. But as you see, again, the core, the mantle, and the crust, notice in Mercury's case that the core is proportionately quite large compared to the other terrestrial worlds. Well, again, being so close to the sun, we would expect Mercury to be composed primarily of heavier elements. Lighter elements would tend to have been dissipated by the fierce heat of the sun. However, even though Mercury is close to the sun, that does not mean that its interior will be hot. But rather, as we said earlier, being a small world, Mercury gradually lost its interior heat, and so its interior is relatively cool. Very little, if any, activity today on Mercury. And as a result, we'll see in our next lecture, the surface of Mercury shows a very ancient surface that has not been changed by geologic activity. As we move on to Venus, we see again here a diagram on the left of Venus, core, mantle, crust, very much like we saw with Earth. But here's a significant difference now for Venus. Venus rotates very slowly, taking 243 days to rotate. Not only that, but Venus is tipped over on its axis quite a bit, almost 180 degrees. And so in that sense, when you think about it, it's almost as if Venus' North Pole is where the South Pole would normally be here on Earth. And if Venus began rotating in the correct direction as Earth does. If you tip it over almost 180 degrees, it's going to appear to rotate backwards. So a very strange world here. Rotating backwards and very, very slowly. Well, this slow rotation has a great effect on Venus. How so? That slow rotation means the core of Venus, even if it is molten, is not moving very fast, and as a result, Venus has a very, very weak magnetic field. Well, what's the consequences of that? We said earlier that Earth's magnetic field protects us and our atmosphere. Well, in this case, Venus' lack of magnetic field means there is no protection for its atmosphere. And as a result, any water on the surface of Venus and in its atmosphere has been broken apart by the powerful radiation of the sun, and as a result, Venus now is quite dry. Truly a very different, very dramatically different situation than we have here on Earth. Let's move on to Mars. As you see in our diagram, Mars again has our typical core, mantle, and crust. Now Mars being a somewhat smaller world, intermediate between Earth and perhaps Mercury or the Moon, again you would expect it to hold on to its heat for some period of time, but then to gradually lose that heat. And yes, Mars has now lost its heat. It has insufficient heat to drive any geologic activity, and so the surface again appears fairly inactive. However, that's not always been the case. There's clear, solid evidence that Mars once was a very different world, much more active geologically and in other ways. In fact, there's clear evidence that there was great quantities of liquid water on the surface of Mars in the past, but none now. So what happened? Well, the key really is that Mars lost most of its atmosphere. It probably started out very much like Earth, thick atmosphere, water on the surface. Why would it lose its atmosphere? Once it lost its atmosphere, there would no longer be water on the surface. So again, how could it lose its atmosphere? Well, once again, the key starts with Mars' smaller size. We said that with that smaller size, it's going to lose its heat a little bit faster, and as it loses its heat, its geologic activity will decrease, but importantly, so will the magnetic field. As a result, very much like Venus, if Mars lost its magnetic field, its atmosphere would then be vulnerable to, again, the sun's powerful radiation. So as Mars cooled and the core motion slows, the magnetic field decreases, and now the sun's solar wind can strip the Martian atmosphere. Once the atmosphere is stripped, we can no longer have liquid water on the surface. So we see a very interesting intermediate case here of Mars, bigger than Mercury, held on to its heat longer, was active longer, but not as big as Earth, and so has now lost its heat, lost its magnetic field, lost much of its atmosphere and its surface water. So I think you can see the important role that size plays in the terrestrial planet's history. Size determines the internal heat. The internal heat not only determines the geologic activity, but it also determines the strength and longevity of that magnetic field. And that magnetic field is crucial to protecting and preserving the atmosphere of a planet. So our diagram here nicely illustrates the progression. At the bottom we see the Moon, the smallest of the terrestrial worlds, and Mercury, again, probably lost their heat very early in their history. Very little surface activity, and therefore their surfaces have not changed much. Really, they're quite ancient. Mars, that intermediate case, held on to its heat longer, but at some point that heat did fade out. Again, the magnetic field did fade out, and the atmosphere was lost. Venus, nearly the size of the Earth, we would expect to remain warm inside. However, you'll recall that the key here is Venus doesn't have the same rotation as Earth. So even if it is warm inside and geologically active, the lack of the magnetic field means that the water was stripped from Venus' atmosphere. Finally, we now can see Earth in context, can't we? We see a world that's large enough to generate heat for long periods, large enough to hold on to that heat, to drive geologic activity even today, and large enough to maintain a very substantial magnetic field that shields not only you and I, but our very, very important atmosphere. So very interesting to be able to summarize and see, again, the context of our terrestrial worlds here, how important size is when we look to the inside of the planets. So let's go ahead and do a summary of what we've discussed in our lecture today. What are the terrestrial planets like? We saw three main sections: a core, a mantle, a crust. Why are they like that? Well, we explained differentiation. Denser material will work its way to the center, affected more so by gravity. Lighter material will float to the surface and establish these three regions. Again, what causes the geologic activity? Well, in a word, it's heat, isn't it? And we saw again, the planets all started out with a large amount of heat due to the impacts of the planetesimals. We then saw that differentiation itself generated a significant amount of heat over time. But as those two earlier processes faded away, only the larger worlds had dramatically enough radioactivity to continue to generate heat and keep them geologically active. So really, to sum up one of our most important points from today, again, larger worlds remain geologically active longer than smaller worlds. So I hope you've enjoyed this little insight into the interiors of the terrestrial worlds. In our next lecture, we'll be back to look in more detail at their surfaces and to understand exactly what we can learn from those.